In this episode, we'll lay the foundations for inferential statistics. We'll meet several important new ideas, the two biggest of which are the standard error and the famous Central Limit Theorem, which is the main engine of inferential statistics. We'll start with a familiar example. Let x be the height in inches of a randomly chosen American man. This is a random variable, and we remember how those work. We can think of any random variable as a faucet, and when we open the tap, values come pouring out. Here, the heights of randomly chosen American men. As we've discussed before, this particular random variable is normally distributed with a mean of 70 inches and a standard deviation of 3 inches. So far, this is old news, but now we'll do something different. Instead of taking one random man's height, we'll take a random sample of many men, let's say 36 of them to be definite, and we'll measure each man's height, and then, and this is the new part, we'll take the mean of all 36 heights. For the sake of argument, let's say this sample's mean height is 69.6 inches. Not surprisingly, this is close to the mean height of the whole population, 70 inches, but we recognize that the particular value of 69.6 was due to the luck of the draw. With another sample of 36 men, we'd likely get a different sample mean. Maybe we'd get 70.1 inches. And of course, the mean of some other sample of 36 men might be 70.7 inches or what have you. Notice what's happened here. The sample mean of 36 heights has become a new random variable in its own right. We have a special symbol for the sample mean when we view it as a random variable, which is Xbar. And of course, since Xbar is a random variable, we can imagine opening the tap and letting values pour out. Each value represents the mean height of a sample of 36 randomly chosen men. And since Xbar is a random variable, we can ask the usual questions about it. First, like every random variable, Xbar has a mean. What is the mean of Xbar? How does it relate to the mean of x? Similarly, every random variable has a standard deviation. What is the standard deviation of Xbar? How does it relate to the standard deviation of x? And more broadly, what does Xbar's distribution look like? Let's consider these questions in a more generalized setting. We can let any random variable x generate a fixed number of values, and then we let Xbar be their mean. If we do so, then Xbar is a random variable in its own right, and it behaves as follows. First, the mean of Xbar is always going to equal the mean of x itself. So in our particular example, the mean of Xbar is the mean of x itself, which we know is 70 inches. There's nothing deep here. When we take random samples of 36 men and average their heights, sometimes the average will be a bit above 70 inches, sometimes it will be a bit below, but all those sample means will be clustered around 70 inches, since that's the average height of all American men. Incidentally, since our green box is being transformed from questions about Xbar to answers about Xbar, I should change its title to something more neutral. Let's move on to the next question. What is the standard deviation of Xbar? The first question we might ask ourselves is the standard deviation of Xbar just the standard deviation of x itself? Well, let's think through the meanings of these symbols. On the one hand, we know that the standard deviation of x measures the typical variation in height from man to man, and we know that men can vary quite a bit in height. On the other hand, the standard deviation of Xbar measures variation from group to group. This should be considerably smaller, because even if we get one or two men of extreme height in a group of 36, their individual extremities will mostly be washed out when they're averaged with all the other men in the sample. So the variation among groups will be smaller than it is among individuals. The larger the groups, the less variation we'll see, since the values of the occasional extreme individuals will be diluted by more and more typical values. There is, in fact, a precise relationship between the standard deviations of Xbar and x. Namely, the standard deviation of Xbar is the standard deviation of x itself divided by the square root of the sample size. A bit of terminology while we're here. The standard deviation of Xbar is often called the standard error of the sample mean. Don't let this confuse you. The little shift in terminology is just a way of reminding ourselves that this is about the variation from group to group, not individual to individual. At any rate, this standard error of the sample mean is the standard deviation of x over the square root of the sample size. Proving this is a bit out of reach in this course, but we should at least be able to see that this formula is consistent with our intuition. For larger samples, our intuition tells us that the standard error should be smaller, since the extremes will get more and more diluted in the averaging process. And a little thought shows that our formula for standard error agrees with this intuition. If n, the sample size, is increased, then the square root of n gets bigger too. But when you divide by something bigger, the result is something smaller. So the net effect is that increasing the sample size decreases the standard error. Okay, let's bring this back to our specific example. When Xbar is the sample mean of 36 American men's heights, what is the standard error of the sample mean? Well, according to our formula, the standard error of the sample mean is the standard deviation of x divided by the square root of the sample size. Since the standard deviation of x is 3 inches and the sample size is 36, our standard error is 3 over the square root of 36. That is 3 over 6, which is better known as half or 0.5. Before we move on to discuss the distribution of Xbar, I want to dwell on the standard error since it's such an important concept. We've been looking at an example with a sample size of 36, and we've seen that in this case the mean of Xbar is 70, since the mean of Xbar is always just the mean of x, and the standard error is 0.5. Notice how much smaller this standard error is than the standard deviation of x. The standard deviation of x, a full 3 inches, is 6 times as large as the standard error of the sample mean. And we see this reflected in the sorts of numbers emerging from the two spigots. The Xbar spigot produces numbers that are clustered much more tightly around the mean of 70 inches. But this all presumed a specific sample size of 36. We've already discussed how increasing the sample size will reduce the standard error, but it may help to see this played out numerically. Suppose we bring in another version of Xbar, in which we take the mean height of 900 randomly chosen American men. What can we say about this new random variable? Well, its mean is still the mean of x itself, which we know is 70 inches. Now for a more interesting question. With the sample size so dramatically increased, what will the new standard error be? Well, we know the formula for the standard error. It's the standard deviation of x over the square root of the sample size. So here, the standard error is 3 over the square root of 900. That's 3 over 30, which is 1 over 10, or 0.1. So this large sample has shrunk the standard error considerably. It's only a fifth of what it was when our sample was 36 men. So if we imagine drawing some values from this random variable, they will be even more tightly clustered around the mean of 70 inches. In our original random variable, x, which gives the height of a randomly chosen man, we could get values as extreme as 64 inches, which is a full half a foot below the mean, without blinking an eye. However, when we moved over to samples of 36 men, the furthest we got from the central value of 70 inches, at least among the numbers I've shown on the screen, was a mere 1.1 inches above that expected value. And when we considered samples of 900 men, the most extreme results we were seeing on the screen were only 0.2 of an inch away from the expected value of 70 inches. Okay, I think you get the idea. Let's get back to our original example with n equals 36 and take up the last question. What does Xbar's distribution look like? To answer this, we'll appeal to a simple result that we'll record in the usual place. If x is normal, then Xbar is normal too. In other words, Xbar inherits normality from x. So if we return to the case at hand, we note that x itself is normal, so Xbar must be normally distributed too. It inherits normality from x. Since we now know that Xbar is normal, let's draw a picture to remind us that we have two different normal random variables here, x and Xbar. X, the height of a randomly chosen man, is centered at 70 with a standard deviation of 3 inches, while Xbar, the mean height of 36 randomly chosen men, is also centered at 70, but with a standard deviation of only half an inch. Let's answer some specific questions about these distributions. Question 1. If we pick a random American man, what's the probability that he'll be over 6 feet tall? This probability corresponds to this area on the distribution of x. The solution here is familiar. We want the probability that x is greater than 72 inches. Since x is normal, we can standardize it and rewrite this as the probability that z is greater than something. To get that something, we subtract the mean of x, 70 inches, from 72 and divide by the standard deviation of x, which is 3 inches. This reduces to the probability that z is greater than 2/3, which a computer or a table will tell us is about 0.25. So about 25% of American men are over 6 feet tall. Now, let's turn to question 2. If we pick a random group of 36 American men, what's the probability that their mean height will be over 6 feet? We can solve this problem in the same way, and it's just as easy, provided we keep track of which random variable we're working with. This is a question about mean height, so we want the probability that x bar is greater than 72. Notice that this will be tiny. If I tried to shade the appropriate region on x bar's distribution, you wouldn't see anything because it's too far into the right tail. We can still come up with a numerical answer since we know that x bar is normal, which means that we can standardize this. This is the same as asking for the probability that z is greater than 72 minus the mean of x bar over the standard deviation of x bar. I repeat, we are standardizing x bar here, so we need to use the mean and standard deviation of x bar, not of x. This is a place where many people make mistakes. Let it be someone else who makes this mistake, not you. Anyway, the mean of x bar is 70, and the standard deviation of x bar is 0.5. A little arithmetic shows that this comes out to the probability that z is greater than 4. According to Wolfram alpha, this probability is about 0.00003. Notice how very different our two answers are. Roughly 1 in 4 American men are over 6 feet tall, but only 3 out of every 100,000 groups of 36 men have a mean height over 6 feet. Okay, let's return to the All About Xbar page for its grand finale, a result called the Central Limit Theorem, which is the heart of inferential statistics. The Central Limit Theorem tells us that even if x isn't normal, x bar will be normal, and this is the magical part, if n, the sample size, is sufficiently large. How large is sufficiently large? This is a somewhat subtle point, and it really depends on how abnormal x itself is, but for our purposes, we'll say that the Central Limit Theorem kicks in if the sample size is at least 30. The Central Limit Theorem seems somewhat miraculous. Why is this true? I'll explain in the context of another example. Let x be the height, now in feet, of a randomly chosen person at Twin Peaks Elementary School. The distribution of x, as you can see, is bimodal. It has 2 hills, a big one that represents the many kids at the school, and a small one which represents the smaller number of adults at the school. Suppose we were to take random samples of 5 people at the school and measure their heights. Here's our first sample. The luck of the draw gave us 5 kids. If we were to make a crude bar graph of their heights, we'd get something like this. 3 of the kids are between 3.5 and 4 feet tall. 2 of them are between 4 and 4.5 feet. I'm leaving off the vertical axis here to reduce clutter, and because, as you'll see, I only care about the general shape of the bar graph. Take another random group of 5. 5 more kids. Let's put up another bar graph for this second group. And let's pick a third sample of 5. This time we get an adult and 4 kids, so the bar graph for that sample will look a little different from the first 2. If our samples were larger, they'd be more likely to look like the full population distribution of x with its 2 hills. For example, suppose we were to take samples of 50 people at the elementary school. In this case, we'd be almost certain to get a range of adults in each sample, as well as a range of kids. Here's the bar graph for one such sample of 50. Here's another. And here's a third. While still very crude, they give a better sense of the distribution of x itself than the samples of 5 did. Now consider the first sample of 50. Suppose that when we measured the heights of its 50 people, we went ahead and formed the mean height in that particular sample as well. And let's say that the mean height was around 4.5 feet. I'm going to put a star at the location of that sample's mean. In our next sample of 50, the sample mean shouldn't be too far away from the first one, but it will be somewhat different. It looks like we had some taller adults in that sample, so maybe they pulled the mean up slightly. Similarly, the third sample of 50 will have its mean height, which will be close to the others, but not quite the same. I'll shrink these to make some room for myself. Now imagine that we take samples of 50 over and over again, recording the results in bar graphs and including the sample means each time. Imagine doing this not just the 7 times that I have on the screen, but hundreds, thousands, millions of times. By the way, these are catch and release samples, so we don't have to worry about running out of people at the school. Now, forget about the bar graphs, leaving only the sample means themselves. Again, I'm going to crunch these up to make a little more space for myself. Each star represents a sample mean of a group of 50 people, and we imagine this sampling occurring again and again and again. Because the random samples are fairly large, they all look somewhat like the full population, and thus they all look somewhat like each other. In particular, their means will tend to cluster around some central value, which is in fact the expected value, the mean, of the sample means. Some of the stars, the individual sample means, will be above this central value, and others will be below, and there's no reason for them to favor one direction or the other. Also, most of the stars will be close to the central value, and the further away we go from this central value, the fewer stars we'll see. What this all means is that if we let the stars fall straight down until they land on an expertly placed table, all these sample means will end up in a heap, with most of them near the central value and fewer as we move away from it on either side. The shape that is emerging is, in fact, the bell curve. This, I hope, gives you a sense of why the distribution of x bar will be normal, even though the distribution of x itself was very far from normal. If so, then you can see why the central limit theorem holds. The central limit theorem is pretty amazing because it establishes a bridge between non-normal distributions and the normal distribution. That way we can often use facts about the normal distribution to answer certain questions about random variables that are not normally distributed. Let's consider an example. Suppose that in Zembla, the mean lifespan is 77 years, with a standard deviation of 9 years. Our first problem: find the probability that a randomly chosen Zemblan lives at least 79 years. We'll begin by defining the relevant random variable. Let x be the lifespan of a randomly chosen Zemblan. We want the probability that x is greater than 79. It's very tempting here to think, I know what to do with this. We just standardize x and write that this is the probability that z is greater than 79 minus the mean of x divided by the standard deviation of x, and so on and so forth. Right? Wrong. We cannot relate x to its z skeleton because we have no idea if x even has a z skeleton. We are not told that x is normally distributed. And in fact, lifespan distributions tend to look like this, very strongly skewed, definitely not normal. So even though we know the mean and standard deviation of x, they won't help us answer the question as matters stand. And we must admit that we don't have enough information to find the probability that we seek. Such is life. Let's consider problem 2. Find the probability that the mean lifespan of 64 randomly chosen Zemblans is at least 79 years. Your first thought might be that there's no way we can answer this, since this seems so much more involved than that first problem, which we couldn't solve. Not so. We can solve this one. Let x be the lifespan of a randomly chosen Zemblan, and let x bar be the mean lifespan of 64 randomly chosen Zemblans. We want the probability that the mean lifespan of 64 randomly chosen Zemblans is at least 79, so we want the probability that x bar is at least 79. Now it's tempting, once again, to try standardizing, to say that this is the probability that z is greater than 79 minus the mean of x bar over the standard deviation of x bar. But can we say this? Is this legal? Well, it's legal if x bar has a z skeleton. That is, if x bar is normally distributed. So the question is x bar normally distributed? X isn't normal, so x bar doesn't inherit normality, but the central limit theorem tells us that if the sample size is sufficiently large, which it is, 64 is considerably bigger than 30, then x bar is normally distributed. So yes, x bar does have a z skeleton, and standardizing it to z is perfectly legitimate. To carry this problem to its conclusion, we'll need the numerical values for the mean and standard deviation of x bar. Well, the mean of x bar is always just the mean of x, which we know is 77 years. As for the standard deviation of x bar, We've seen that this is the standard deviation of x itself over the square root of the sample size. In this case, that translates to 9 over the square root of 64, which is 9/8, or exactly 1.125. When we substitute these values in, we get this, which reduces to the probability that z is greater than 1.78. Wolfram alpha tells us that this is approximately 0.04. That is, only 4% of such samples will have a mean lifespan of over 79 years. And that is all. If you understand the handful of ideas and results in this All About Xbar box, you should be in good shape. See you next time.